Last time we start to talk about how to handle collisions in hashing. We have last hour we have seen one of the methods, which is open addressing. Now we are going to talk about the alternative method, which is called chaining. In chaining, we keep a list for each table entry. So, for example, for table entry 3, we keep a list, and in that list, the elements that are hashed to index 3 will be kept. So, if there is a collision, there was a collision, since there are 2 elements in this linked list. 2 elements, Harry and Pete, are mapped to index value 3. So these 2 values are available in the linked list referenced by table entry 3. And in this position, we have 3 elements. All of them are mapped to index 4. Both Tom, Dick, and Sam are mapped to index 4 and put into the linked list referenced by table element 4. So each table element refers to a linked list, and that linked list contains all the items hashed to the same table index. This linked list can be called as bucket. So this operation, this method would be called bucket hashing as well. It's usually called as chaining, but sometimes in some references you can see bucket hashing as well. So this is a simple way of resolving collisions. If there's a collision, keep a linked list and put everything collided into this linked list. It has some advantages over open addressing. In open addressing, each table entry can keep just one value in open addressing, and if it is occupied, we should try another index value. So while searching or inserting a new element, we have to try several locations, and in that locations, even if it is some values which are hashed to another index is seen, still we have to go through that values. So we have to look for elements, go through elements that are not hashed to the same index, but in chaining, we have to examine the elements only hashed to the same index position. Only items that have the same value for their hash code are examined, which are in the same linked list. Also, you can store only one element in each position in the open addressing, but you can store several elements in the linked list. You can store more elements in the table, in other words, than the number of slots, right? You can insert the element in the appropriate linked list. For example, if an element mapped to 3, then it should be inserted in this linked list. But you can insert anywhere in this linked list, either at the beginning or at the end or at the middle, doesn't matter. So you can easily insert anywhere in the linked list. Once you determine the item is not present, you can insert at the beginning or at the end of the linked list easily. Anywhere is possible. In open addressing, you have to replace the entry you found with a deleted item. It was a problem, remember? You have to go through, probe through that item even if it is deleted. But in chaining, you can simply delete the item from the corresponding linked list. You don't need to worry about deleting and putting demo item in its place. So removal is simpler in chaining. As I said, whether we use chaining or open addressing, the performance of the hash table depends on the value which is called load factor. Load factor is the number of filled cells divided by the table size. If you have larger load factor, then the performance of the hash table is lower. So when the load factor gets larger and larger, the performance gets lower and lower. So for the better performance, we should keep the load factor low and usually below some threshold. So of course, if there is no collision, the performance of the search and retrieval or insertion or deletion or all will be constant time, regardless of the table size. That's important. Whatever the table size is, if there is no collision, you have constant time operation. It is regardless of table size and regardless of the number of elements in the table. If there is no collision, the performance is constant time. But it is not easy to get that property. Collisions may not be avoided completely. There may be collisions. And in that case, to reduce the collision probability, we have to keep the load factor lower. There are some figures, there are formulas available in the literature, in papers. For example, Donald Knuth is one of the famous scientists in computer science. He derived a formula for expected number of comparisons, expected number of probes to perform in finding an item that is in the hash table. So if the element is in the table, the expected number of comparisons is can be calculated by this formula. Of course, it is for open addressing and linear probing. L is the load factor. So with a probe, if L is 5/11, right? If there are 11 cells in the table and 5 of them are full, then 5/11 is the collision probability actually. And 1 minus L is the probability of not collision. So if you make a probe, the probability of not having a collision, probability of finding an empty cell is 1 minus L. And 1/1 minus L is the number of probes until we find an empty cell, null cell. This is the expected number of probes to find an empty cell. We incremented by 1 since we always perform a probe for the first probe. First probe always performed. And then we divide by 2 since we may find the element since it is in the hash table. Since it is in the hash table, we find that element on the halfway through the whole sequence of probes. So this is the formula that is provided by Donald Knuth. And you can use this formula to find a number of probes for several cases, so several load factors. For example, if L is 0.5, this value is 0.5. This value is 1/0.5, which is 2. So 1 plus 2 is 3/2. So C is 3.2. 1.5 probes are performed in search operation in of course open addressing with linear probing if load factor is 0.5. If load factor is 0.1, this is 0.9, right? So 1/0.9 is almost 1. It's very close to 1. So 1 plus this value will be 1.9/0.9. And over 2, it is like 1.9/1.8, right? So C is 1.9/1.8. It is very close to 1. So when you decrement the load factor, the value of C gets closer to 1. When you increment the load factor, for example, if L is 0.9 in this case, this value is 0.1. So this makes 10 over here. 10 plus 1 is 11 over 2. So 11 over 2, like 5.5. More than 5 probes is necessary if the load factor is above 0.9. And it gets larger and larger while the load factor increases. Here you see the number of probes. So if 0.9 is 5.5, and if it is 0.95, it becomes more than 10 and gets larger. Of course, when the load factor is 1, if L is 1, this value will be 0, this value will be infinity, etc. So L shouldn't be 1 in this formula. Otherwise, the number of probes will be infinity. Infinitely many probes are required. Okay, this is for open addressing, as I said. For chaining, so the load factor is the average number of elements in a linked list. So in a linked list, L many elements. And in a linked list of L elements, looking for a value requires, remember, this many operations. We find element almost at the halfway through all the values. So on average, half of the elements should be searched for, looked for. So the number of probes is this big. This 1 comes because the first element has to be compared anyway to find it. So in chaining, we must examine the table elements corresponding to the data items hash code. And on average, we have to look for half of the items in the list. So this is the formula. For example, if L is 1, number of probes is almost 1.5. As you see, L could be more than 1 in chaining. We can have L to be true. In that case, C will be true as well. Okay, so we can have a load factor more than 1 in chaining. On the other hand, in open addressing, a load factor of 1 is not possible, or anything more than 1 is not possible. Okay. Here is the table for different load factors. Of course, here the load factor is not more than 1, since if it is more than 1, linear probing has no meaning. The number of probes cannot be calculated for linear probing if the load factor is more than equal to or more than 1. And as you see, the increase in number of probes in chaining is a lot slower compared to the increase in number of probes in linear probing. Since we do not need to go over the elements with the different index values. The most important reason here is, for example, if we have to look for Pete, which is index to 3, we look for this position. Harry is index to 3 as well, but we look for Tom, which is not indexed to 3rd position. Dick, Sam, not in 3rd position. So even if the index value is different, we have to go through them in open addressing. But in chaining, we only have to go through Harry and Pete. That is a lot better, as we said before. So this makes the number of probes less for chaining. Okay. So when we compare the performance of the hash table with sorted array and binary search tree, for example, in sorted array, the search operation can be performed with binary search. Since it is sorted, we compare in middle element, etc. Continue with the left or right half of the array, and the running time will be logarithmic, right? So if there are 128 elements in the sorted array, we have to perform 7 probes at most. Log 128 is 7, right? And 7 probes requires, if to be able to have 7 probes in linear probing, a little more than 90% load factor of 0.9, a little lower than load factor of 0.9 gives that many probes. Okay, to have 7 probes, hash table of any size that is 90% full is requires 7 probes. In binary search, the worst case running time is linear, but average running time is logarithmic. So in for this, these are for the insertion and removal, but for search, hash table is constant time expected and linear time worst case. Sorted array, here we have unsorted array. In unsorted array, linear time worst case, right? And average case linear as well. Average linear as well. In binary search tree, insertion, this is for search operation, remember? Binary search tree, search operation will take O log n for average case and O n for worst case, right? And for the sorted array, of course, sorted array, search operation will take logarithmic time. Insertion and removal should take or linear time in worst case as well, since we may need to move that many elements. So when you look at the performance, this constant time, expected constant time, is a very good running time for the hashing, and it doesn't depend on the number of elements in the table or table size, but the load factor. Load factor is important for the running time in hash table. So when we look at the storage requirements, the performance of hashing is better than binary search if the load factor is less than 0.75, even less than 0.9. However, in a lower load factor, we have lots of empty cells. On the other hand, sorted array doesn't have any empty cell, right? So based on the storage requirement, sorted array may be better. When we compare it with the binary search tree requires 3 references, right? A reference for the item, left subtree, and the right subtree. So the storage requirement for the binary search tree is worse than hash table with the load factor 0.75, since these 3 references requires a lot of space, 3 times the space of the number of elements. But here in 0.75 load factor, we have 1.5 times the number of elements is used for the space. So, so for the binary search tree, 3n space is required. For the hash table with load factor 0.75, we require 1.5n memory space. N is the number of elements, right, in a table. So the table size should be 1.5 times of the number of elements. Almost 1.5 times, since the load factor is 0.75, is n over 1.5n, right? One over 1.5 is 0.66. To be able to have 0.75, it is like 1.4 or so. Okay. When we compare open addressing and chaining based on the storage requirements, so in open addressing, number of references we store in the table is the only thing we have to store. So if n is the table size, n references are stored in the table. But for chaining, the number of references also depend on the load factor. So L is the average number of nodes for each table entry. And if we implement the linked list for each table entry, the linked list here can be implemented as linked list of Java. Remember, the linked list of Java is double linked list. So besides item, we have next and previous references. But if we have our own single linked list, we can reduce the number of references. We can only use item and next, previous can be avoided. So 2 references would be enough. So in chaining, the number of references stored in the table for the structure will be n for the table, for this one, and 2L for the references here. Okay. For example, in open addressing, if we store 60,000 items in the hash table with load factor of 0.75, table size should be 80,000, right? So this, for each entry in the table, we should store just one reference. So the number of references stored in the table would be 80,000. What is the runtime performance? The expected number of comparisons for 0.75 is 2.5. As you remember from here, 75 is 2.5 for linear probing. If we should have the same performance chaining hash table, remember for chaining the number of probes is L or 2, right? If we put 2.5 as number of probes, then load factor will be 3, L will be 3, right? So if load factor is 3, we have the same number of comparisons. And if the load factor is 3, the number of entries in the table will be 20,000. So we have 20,000 entries in our table. But we have from here, we have reference for the elements as well. So we have 20,000 storage spaces, 20,000 references for the table. And we have this many nodes in the table. And for each node, we have 2 references. One is for the item, one is for the next. So 2 times 60,000 plus 20,000 from here is 140,000. When you compare with open addressing, it was 80,000, remember? It is a lot more, 175% more storage space is required for chaining. So chaining is worse compared to open addressing in terms of the memory, but its performance is better in terms of running time. Okay, next thing we are going to talk about is how to implement hash tables. This is the hash map interface, as you see, but we are going to have our own interface, simpler interface, containing only these methods. These are similar to methods in hash map interface in Java. As you see, get method takes a key as a parameter and returns the value for the key if it is available, and null for if it is not, etc. You can check them out. They are very similar to hash map abstract data type in Java. To be able to implement this interface, hash map interface, we have to have an table entry class. At each table entry, we have to store the key and value information. Key should be unique in table, and for each key, there should be specific value stored in the table. So each entry keeps true values, key and value. The types are generic, as you see. And it has a constructor, true parameter constructor, and getters, setters for the key and value. There is no setter for the key, since the entry is specific for that key value. So if you would like to change the key, you have to create a separate entry for different keys. So there is no setter for the key value, but we can change the value for the same key. So we have a setter for the value that is required to implement this put operation. If the key is available, we just set the value for that specific entry. So the implementation is simple. This is an inner class for the hash table. So as you see, it is defined to be private. And inner table, inner class. Key and value are true data fields. And simple methods, constructor and getter setters. We are going to talk about true implementation of the hash table. One is the open addressing implementation. The other one is chaining implementation. In open addressing implementation, here, hash table open class that implements the KW hash map interface. This interface will be implemented by the class hash table open. In this class, we have to keep a table of entries, which is an array of entry. As you see, entry type array is used in this hash table, which is called table. Table is the array. A constant value for the starting capacity, initial capacity, and load threshold, maximum load factor is, these are two constants. One of them is static, the other not. The other is not static. You define it during construction, but you will not change it afterwards. Okay, number of keys and number of deletes are two data fields that are necessary. We are gonna keep a number of key values, key value pairs actually inserted into table. This integer number of keys doesn't include the deleted elements. Number of deleted elements will be kept in this num_deletes data field. Also, we have to have a dummy element that will be used in place of deleted values. This is the dummy element, dummy entry. It's a special object to indicate the entry has been deleted. Okay. So as you see, this is the implementation of KW hash map interface through hash table open. Yeah, we have table, some constants, number of keys, number of deletes, and a deleted entry is the entry which is null for both key and value fields. Constructor will create a table, an array of size start capacity. Of course, it is entry array, right? Okay, to be able to perform the operations over here, to be able to perform most of the operations here, we define two private methods. One is find, the other one is rehash. These are private methods. Find method takes an object as a key value and returns the index value, integer. And that index value is the index that key value is the element equal to key value resides in the table if it is present in the table, and it returns an index of the empty slot, first available empty slot if it is not available. So this is the code, the algorithm for the find operation. We use hash code and mod operation based on table length to calculate the index. Since the result of hash code would be negative, the index could be negative in this case. If it's negative, we add table length to make it positive and real index value in the table. And while the entry at the index is not empty and not equal to the key, we continue incrementing the index value. At the end, either the table index will be empty, which is null. That means the key is not in the table, or the key is equal to table index, which means key is found in the table in index position, and we return index. But you should be careful in incrementing the index, since the table should wrap around. If table index is greater than the table size, we should set the index to be 0, or we can perform mod operation also based on table length for after increment operation. But this would be better probably. So this is the code for this operation. Find takes a key which is of type object. As you see, we use the equal method of the key. Since it is of type object, it takes an equal method and checks whether this key value at that index is equal to the provided parameter key over there. First, it has to have hash code as well. We calculate the hash code and perform mod operation to calculate the index, and if it is less than 0, we increment it by table length to make it positive. Then if while the table at that position, the element at that position in the table is not null and not equal to the key value, we increment the index. And don't forget to wrap around. After the while loop is terminated, we return the index. As you see, the one-to-one implementation of this algorithm. Our time is up, so I will stop here and continue on Thursday. We will not have a PS session tomorrow. PS will be on Friday. So on Thursday, we are gonna go over the implementation for both open addressing and chaining, and we are going to talk about the Java's hash map and hash set classes as well, and finish up this chapter. Okay, this is it for today. If you have question.
Hocam soru değil de bir maruzatımız olacaktı bizim.
Gene ödev değil mi?
Evet hocam. Hocam çok sıkıştık.
Yani bu ödev meselesi bir türlü bitmiyor ya.
Hocam geçen hafta çok sınavımız vardı. Pazartesiden daha dün bir tane büyük bir olasılık ödevimizi teslim ettik. Yarın sınavımız var. Perşembe günü quizimiz var. Cuma günü ayrı bir labımız var. Pazartesi sistem sınavı falan filan var. Çok yoğun oldu bu dönemler şu an. Biraz uzatma
Yani
şansınız var mı?
bakalım birkaç gün uzatırız belki.
Sağ olun
Pazar
hocam. Teşekkür
gecesine
ederiz.
koymuştum zaten değil mi? Pazar gecesiydi. Tam bir
Cuma
hafta vermiştim.
30'una koydunuz galiba.
Evet hocam, Cuma gecesi.
Cuma gecesine. 23'ünde verdik. Cuma gecesine koyduk. Pazar gecesi desem
Pazartesi sınavdan sonra olsun hocam. Salı olsa olur mu? Pazartesi sınavı da atlatalım.
Salı gecesi. 4'üne istiyorsunuz. Tamam, 4'ü gecesi olsun.
Çok sağ olun hocam. Çok teşekkür ederiz.
Teşekkür ederiz hocam, sağ olun.
Okay.
Teşekkürler.
Bir daha ödev vermeye hakkımı saklı tutuyorum ama yani biraz overlap olma hakkımı saklı tutuyorum. Okey, 4'üne update
Ederiz hocam.
edeceğim. Okey, görüşmek üzere.